Next, we need the cross correlation A transpose times X. Since we now just have this one sample in the future as our target vector, this converges to the autocorrelation vector starting at leg 1. So together we get the solution for our prediction filter given by here. So a system which produces the prediction error, for instance, part of an encoder as an output is the following. So here we have our original signal. Here we have our error, which is our original minus the predicted. Here we have a delay, and here we have a transfer function. So here x of n is the signal to be predicted. H of z is our prediction filter, whose coefficients are obtained with our Wiener approach in the last lecture slides. So here h of z is simply the z transform of h, which is given by this correlation. It works only on only past samples. That's why we have the delay element by one sample, z to the power of minus 1 before it. And x hat is our predicted signal, and e is our prediction error signal. Hence, our system, which produces the prediction error, has the z-domain transfer function of this equation here. So this can be an encoder. Observe that we can reconstruct the original signal x of n in a decoder from the prediction error e of n with the following system. Now we have here the prediction error, and we want to obtain the original signal. It will be the prediction error plus the predicted signal, and here again we have z to the power of minus 1. We have our h of z. So remember that encoder computed the error, so it was the original minus the predicted. The feedback loop in the system is causal because it only uses past already reconstructed samples. And observe that this decoder transfer function is given by this here, which is exactly the inverse of the encoder, which was to be expected.